So in this part of the lectures on experimental techniques, I want to go and talk a bit about control of an experiment or system control. So quite often you want to actively control some kind of parameter in your experiment. So that might be a temperature, a pressure, a position, a magnetic field, a variety of different things. So to do this, you need some kind of control system that takes in some measurement reading and then computes, compares it to some kind of set point, and then computes some kind of control value or adjusts some kind of controlling parameter to try and correct for any deviation of the thing you're measuring from your desired value. And so I'm going to introduce you to some of the kind of common aspects that are used to go and do this. So for an example, let's go and think about trying to control the light level in a room. So we have a room. It has a light switch. And it's got a window. And we're going to have some kind of light sensor in it. Okay, so the simplest form of control is simply to have a light switch that if you decide it's too dark, you turn the light on, and if you decide that it's too bright, you turn the light off again. So this is a very simple on-off control. So if we make a graph of the light level, and we'll imagine that over the course of the day, our light level might be varying. So left to our own devices, okay, I guess this is overnight because I've got my light going down and then coming up again in the morning. And what we could do is we could simply go and say, let's have some kind of threshold. It's not going to be very visible. So there's some kind of threshold. And we say that if our level of light is below the threshold, then we're going to turn the light switch on. So our light would go on, and then when it comes down, it goes off again. And that's all good. Okay, that's fine, no problem there. But the problem, of course, is that what's going to happen is that we're going to turn the light on, and all of a sudden, instead of just carrying on that nice smooth trajectory, it's going to get bright again. So then we'll turn the light off. And so what will tend to happen is rather than just the light staying on all the time, and the trajectory following that nice pattern like that, we turn the light off, and immediately the light level goes too low. So we turn the light on. Whoops, come up, and the light goes on. And you can see what happens is that our level of light is going to go and fluctuate wildly backwards and forwards like that. And the light's going on and off and on and off and on and off and on and off. And that clearly isn't great. And of course, if the system gets made very, very fast to respond, it sort of gets a stroboscopic effect of your light. So that's clearly not a desirable situation. So how can we improve the matters? Well, we could think about having a system where we have one light level that you turn the light on at, and a different light level you turn it off at. So if we have a nicely smoothly varying level of light like that normally, and we put a level of light at which we want to turn the light on, and we could have a level of light at which we want to turn it off. It's a bit brighter. And so in this situation, what would happen is when the light level crossed the turn the light bulb on moment, we would turn our light on. And if our light bulb isn't so bright that it exceeds the off threshold, then it would reach some kind of steady state like that. And so it would follow that kind of a trajectory. And our light is on until we cross this point here, where we turn the light off again. And so we've at least managed to stop the thing going on and off and on and off and on and off and on and off. So by adding this hysteresis to it, we've managed to go and stop the thing from going on and off. We're able to control the light level within a reasonable band. Of course, the problem is that if our light is bright enough to make a significant difference, we might go to the point where turning the light on takes us past the threshold where we want to turn it off. So there is a limit to how tightly we can control that level of light. We have to accept it's going to lie somewhere in this band here, and the stronger and more powerful our light is, the bigger that band has to be. Okay, so what can we do about this? Well, what we could do maybe is, instead of just having an on-off switch, we could have a dimmer in our system. So what that would mean is that the light wouldn't just go massively on and massively off. It would respond to how different the level of light was according to, compared to the set point. So let's think about how that would work. So what we have is we have a level of light and we have a set point. And at some stage, light goes below the set point, like so. So what we do is we define an error, or a size of signal we're interested in seeing. I'll call that epsilon, and that is the light level we measure minus the light level of the set point. And what we do is we arrange for our light bulb to be arranged on a dimmer. So we have a, I'll call that L for light level, and that is going to be proportional to the error, to the difference we want between our set point and our target value. Okay, so this is something that's called proportional control, and the bigger the difference we've got, the more the light gets turned on. And doing that, you'd hope that it goes and tunes itself nicely. But the problem is with this is that, okay, yes, at least the light level now doesn't flick on and off massively, and we can define a single level over which we want to control that level of light, but it doesn't necessarily guarantee that we're going to end up with the light stabilizing at our set point. So what we'd find in this case probably is that it would go up, but it might stabilize at some value which was different from our set point, because it simply could be the case that we need our light to be on to some amount. We're going to have a finite amount of uncertainty there in order to get the light to stable. It'll find some stable value that's not actually quite on our set point. So although we're stable and we're not massively swinging backwards and forwards, we're not actually reaching our set point. So what you do is you sit there and think, well, what we could do is we can have it also look at the difference summed up over time. So we could add another term which depends on the integral of that difference between our actual value of light and our set point. And the effect of that is going to be that rather than stabilizing at the wrong level, it will eventually, we hope, line up. But the problem is that it doesn't necessarily have to do that. What it could do quite easily is to oscillate. And so yes, on average, it's reaching our set point, but that disguises the fact that it's gradually oscillating, getting darker and brighter and darker and brighter. And that's not really what we want going on either. So then we think, okay, how are we going to go and get rid of this oscillation? So what you can notice is that although the integral is going to average out over time, and the average difference is averaging out over time, the rate of change is always non-zero. So we can simply add another term, which is proportional to the rate of change of the difference between the value we want and the value we've actually got. And the effect of that combined should be to damp the oscillations out and return it to where we want. Okay, so to understand what might happen then, let's think about a situation where our target, we change our target. So we start off with a low target, and then we suddenly make it a brighter target. So we want the light level to suddenly increase. And in this system, what will happen, if we just had the proportional term, it might do that. If we have the integral term and the proportional term, it'll do that. And if we get it just right and have the differential term as well, then it does a damped oscillation like that. Now, one of the things you might want to look at here is, if you actually look at the terms in this equation, then what you'll see, if we differentiate this equation with respect to time and look at the rate of change at which we're turning our light up and down, then you write down an equation, second order differential equation that looks like that. And if you look at this term, then you suddenly realise that that is in fact describing damped harmonic motion. So you've got the second differential with respect to time, and you've got the linear term, you've got the term there, which is the actual the thing you're interested in, and then you've got a damping term here as well. So this is why this looks like a damped harmonic oscillation, because that's exactly what it is. And now that gives you immediately a clue as to what to do with these three constants Pi and D. Because what you're trying to achieve is you're trying to achieve a system where the system reaches that steady, accurate state as quickly as possible. And that means you're looking for a critical damping situation. So if you remember your first year waves course, you looked at damped harmonic oscillators and you had this critical damping concept. So if you set the values of these constants correctly, you can achieve this critical damping, and that's the optimal way of controlling it. If you make the damping too big, then you'll get a system which never actually ever reaches your target point. If you set the damping too low, then what will happen across these constants is the thing will oscillate and ring, but there is an optimum set of these constants that will give you that critical damping, give you the best possible control. So this is called a PID control system, surprisingly enough, after the three constants. And this type of control logic you find in many, many experimental situations. Anything from dealing with the sort of cryostats I deal with, to dealing with mechanical motion of systems. So if you're trying to move a large mechanical object, they tend to have a PID control. Nanoscale objects, so in an atomic force microscope, we have PID control loops running in order to create damped oscillations. If you're trying to control a heater, quite often you'd end up with a PID control in it as well. So many, many different types of situations, but they all have the same maths. And the logic of what you're looking for is to be able to control these various constants in order to achieve that critical damping. Now, in many systems, in fact, it turns out that you can get perfectly adequate control with just a P or an I, sometimes even just a P. But in other systems which are more prone to oscillate naturally, then you need to have the full three P, I, and D terms in order to get the full control. So you'll quite often see something referring to a PID loop, and that's basically what's going on here. And this is one of the most common ways in which you can set up a control system. There are then, of course, more sophisticated variants which start introducing things to do with the rate at which you're controlling, the maximum rate at which you can control the parameters. But the basic logic is this, and it's the same maths as you've done for a simple damped harmonic oscillator.